In this video, we're going to derive the rocket equation. It's a simple form of the rocket equation that we'll develop here because we're going to neglect aerodynamic drag on the rocket. We'll also neglect the effects of overcoming gravity in launching a rocket from, say, the Earth. However, we can make some simple corrections later on for these effects. So let's start with a sketch of a rocket flying through a perfect vacuum where there's no gravitational influence. We'll start by giving ourselves a coordinate system. So let's say that's x, and here's our rocket. We'll say that the rocket mass is mr, and the velocity of the rocket is going to be vr. Let's say that we've got the propellant being ejected, and we'll say that the velocity that propellant is ejected relative to the rocket is going to be v subscript p, and the rate at which we're ejecting that is going to be dmp dt. So a couple of assumptions. First of all, we'll assume that vp, and just make it clear that vp is the velocity of the propellant relative to the rocket. So just making that point that it's the relative velocity, and we're going to assume that that is constant during the period that we're going to be looking at. Let's also, as I said, neglect aerodynamic drag and the effects of gravity. And with that, we can start off with our momentum considerations. We saw from conservation of momentum that we could relate the mass ejection to the effective force on a rocket or on any body ejecting mass. And we saw that come out in the form that said that effective force is equal to negative the rate at which we're ejecting mass, dmp dt, and the relative velocity with which we're ejecting that mass, vp. In our sketch here, we've got that vp is in the negative x direction. So therefore we can say that the thrust and we'll write that as the thrust, and it's going to be in the x direction, is going to be minus the rate at which we're ejecting the propellant, dmp dt, and we're putting that out in the negative x direction, so it's a minus vp. So that means we get vp dmp dt is the effective force due to the ejection of mass. We can note another important point here about the rate at which we're ejecting mass, our dmp dt. As we're ejecting mass out through the rocket's nozzle, the mass of our rocket is decreasing, and we can equate dmp dt to negative dmr dt, because as we eject propellant, we reduce the mass of the rocket. So if we put these two things together, we can say that our thrust generated by our rocket is going to be minus vp times dmr dt. Now we can also say that the thrust is the mass times the acceleration for the rocket. So our mass of the rocket, we're saying, is mr, and the acceleration is the rate of change of the velocity of the rocket with respect to time. So therefore, we've got two expressions for the thrust which we can equate. So we can say that mr dvr dt is equal to minus vp times dmr dt. Let's write this in the following way. Let's write it as dvr is equal to minus vp times dmr over mr. So that gives us an equation in a differential form. So let's see if we can integrate this from an initial state, which we'll call state 0, to some final state, which we'll refer to as state f. So the left-hand side, we integrate that from 0 to f, and that's the integral of dvr, and that must equal the right-hand side, which we're going to integrate from state 0 to state f, and that's going to be dmr over mr. You can see that I've been able to take the vp out of the integral because we're assuming that vp is going to be constant during our period we're considering. So let's slide the screen down. And our left-hand side, the integral of dvr is just going to be vr from our initial to our final condition. That must be equal to minus vp. Now the integral of dmr over mr is log mr, and we're taking that also from the initial to the final state. So the left-hand side becomes vrf minus vr0, the final velocity of the rocket minus the initial velocity of the rocket, is equal to minus vp times log of the mass of the rocket finally over the mass of the rocket initially. Just slide the screen down again, and we'll write this as, we'll write our rocket equation in two forms. The first form is going to be out of what we've got here. So the change in velocity of the rocket is equal to the velocity with which we're ejecting the propellant times the log of the initial over the final mass of the rocket. And you'll notice that I've got rid of the negative sign there by swapping over the m0 over mf from mf over m0. A second form that is also quite useful is relating the final mass over the initial mass, and that comes out in terms of an exponential of minus 1 over vp times delta v. So these are the two useful forms that we'll refer to as the rocket equation. So let's just look at that. First of all, let's look at this first form here, and we're going to have that the if we want to increase our delta v, so how much change in velocity we can get, what we'd like to do is increase our vp. So let's note that to get more delta v, we'd like to increase the velocity with which we're ejecting the propellant. The second point to note is that the delta v varies with the logarithm of m0 over mf. So let's say we also see that delta v varies as log m0 over mf. So therefore, if we wanted to double our delta v, then we'd have to have 4 times the initial mass for the same final mass. So to double delta v, we'd need 4 times m0. And so this shows us an important point, which is that there are diminishing returns as delta v increases because we've got to get our mass going up very rapidly to get a bit more delta V out of our rocket. Before we go on to apply this rocket equation to look at launching satellites into orbit around the Earth, in the next video I want to introduce an important performance parameter for aerospace propulsion systems, a specific impulse.